Lesson 22, Percentile. The percentile is a measure of position of a particular data value relative to all the other data. The percentile measures the position of a particular data value by indicating the percentage of all the data that is less than that value. For instance, a newborn baby measuring 21 inches long was reported to fall at the 93rd percentile for length of newborn babies. This result indicates that 93% of all other newborn babies are less than 21 inches long. Thus, this baby would be longer than most newborns. For instance, a newborn baby weighing 7 pounds 6 ounces was reported to fall at the 46th percentile for weights of newborn babies. This result indicates that 46% of all other newborn babies weigh less than 7 pounds 6 ounces. Thus, this baby's weight would be considered fairly typical for a newborn. When the percentile for a particular data value is high, that is, near 100%, the position of that data value relative to all the other data is considered high. When the percentile for a particular data value is moderate, near 50%, the position of that data value relative to all the other data is considered moderate. When the percentile for a particular data value is low, that is near 0%, the position of that data value relative to all the other data is considered low. Percentiles are denoted by the symbol P sub k. Hence, when k% of the data are less than the particular data value x sub I, the result is expressed as P sub k equals x sub I. For the newborn baby measuring 21 inches long, P sub 93 equals 21 inches. Because the baby measuring 21 inches long falls at the 93rd percentile. For the newborn baby weighing 7 pounds 6 ounces, P sub 46 equals 7 pounds 6 ounces. Because the newborn baby weighing 7 pounds 6 ounces falls at the 46th percentile. In statistics, the 25th percentile is often referred to as the first quartile. The first quartile is denoted by Q sub 1. Thus, P sub 25 is equivalent to Q sub 1. That is, saying 25% of the data is less than a particular value is equivalent to saying 1/4 of the data is less than a particular value. In statistics, the 75th percentile is often referred to as the third quartile. The third quartile is denoted by Q sub 3. Thus, P sub 75 is equivalent to Q sub 3. That's because saying that 75% of the data falls less than a particular data value is equivalent to saying 3/4 of the data values are less than a particular data value. The median is actually the 50th percentile, or second quartile. Thus, MED, the median, is equivalent to P sub 50, the 50th percentile, which is equivalent to Q sub 2, the second quartile. The median measures position where half the data values are less than. Thus, P50, the 50th percentile, is exactly what the median is measuring. There are two components to a percentile: the particular data value x sub I that separates the lower k% of data from the upper 100 minus k% of data, and the value of k that represents the percentage of all the data that is less than the particular data value x sub I. As a result, there are two types of percentile problems that can be solved. One type of problem is to determine the percentile k corresponding to a given data value x sub I. So in these types of problems, we're given the data value x sub I, and then we work to solve for the k, that is the percentile. Another type of problem is to determine the particular data value x sub I corresponding to a given percentile k. In these particular problems, we're given the percentile k, and then we work to solve for the particular data value x sub I. To determine the percentile k corresponding to a given data value x sub I, first we need to sort all of the data from the minimum to the maximum data values. Because percentiles are measuring position by indicating what percentage of the data is less than a particular data value, we need to sort all the data in order to know which values are less than and which values are greater than. So when we have the original raw data, it's the result of a random sample, so the data comes in some random order. So we use the notation x sub 1, x sub 2, and so on and so forth, all the way through x sub n, to denote the data collected in our sample. But these data values will occur in some random order. So we need to sort this data from the minimum to the maximum data value. So let's just say we do that, and we'll get this result. Because every random sample is different, the ordering of the particular data values in the sorted list of data will also be different. So we will use a different notation to indicate data that's been listed in sorted order, that is from minimum to maximum. The notation is to use parentheses in our subscripts. So x sub 1 in parentheses, x sub 2 in parentheses, all the way through x sub n in parentheses is indicating our sample data in sorted order from the minimum data value, where x sub 1 in parentheses always indicates the minimum data value in the sample, through x sub n in parentheses, indicating the maximum data value in the sample. And then any particular data value x sub I can take on any position in the sorted list of data, let's say x sub l plus 1. So now that we've sorted all the data from the minimum to the maximum data values, the second thing we need to do is calculate the percentile k by determining the percentage of all the data that is less than the data value x sub I. So let's say the particular data value we're finding the percentile for, x sub I, is located in the x sub l plus 1 position in the sorted list of data. To calculate the percentage of the data that is less than, we need to count the frequency of data values that are less than that value. So the data value x sub l plus 1 in the sorted list of data has l data values less than it. Then we could turn that frequency into a percentage by dividing by the total and then multiplying by 100. So the percentile k is given by the formula k equals L divided by n times 100%, where L is the number of data values less than that particular data value x sub I, and n is the total sample size. The result is always rounded off to the nearest whole percent. So k, percentile calculations, are always rounded off to the nearest whole percent. That is, we never leave the result in a decimal or fraction form. K, percentiles, are always written as whole numbers only. Now for the other type of problem, where when we're given the k, we try to find the particular data value x sub I. So to determine the particular data value x sub I corresponding to a given percentile k, first we need to calculate the value L by determining the number of data values necessary to be less than the particular data value x sub I for the given percentile k. This is done by using the formula L equals k over 100% times n. This formula is derived from the previous formula we just mentioned, because basically these are the same problems, just working in different directions. So the formula we had in the previous problem, k equals L over n times 100%, to do the opposite problem, we need to solve for L. And to do that, we'll do all the inverse operations in the inverse order. For example, instead of multiplying by the 100%, we'll do the inverse and divide by 100%. To keep everything equal in the equation, we must do the same thing to both sides of the equation. So the 100% divided by 100% is 1, and so now we're just left with the L divided by n. To solve for L, we'll have to do the inverse of the divide by n, which is multiply by n. And again, to keep everything equal, what we do to one side of the equation, we do to the other. The n divided by the n is 1, and that's how we solve for L. L is equal to the k divided by 100% times n. Second, locate the piece of k value in the sorted list of data based on this calculation of the L number that we did in the first step. If the result of calculating L is a whole number, the value for p sub k is given by the midpoint of the Lth and the L plus first data values in the sorted list of data. This is calculated by adding up those two data values and dividing by 2. So if you look at the sorted list of data, this p sub k percentile is the midpoint between the Lth and the L plus first data value in the sorted list of data. That particular percentile has exactly L data values less than it, and the remaining n minus L data values greater than that. And having L out of the total of n data values less than that gives us k% of the data less than that percentile p sub k. And the remaining 100 minus k% of the data values will be greater than that p sub k. This precise separation of the data, getting exactly k% of the data values less than the percentile p sub k, and the remaining data values greater than that value, can only be accomplished when the calculated L value is a whole number only. If the result of calculating L is not a whole number, it is not possible to determine an exact kth percentile for this data. Instead, an approximation is chosen by selecting the data value in the next higher whole number location in the sorted list of data. So if the calculation of the L value results in a value that is not a whole number, that is some decimal, then we need to change the L value to the next higher whole number in the sorted list of data to locate our percentile. So in the sorted list of data, x sub 1 parenthesis through x sub n parenthesis, if we were to calculate the L number and get some decimal value of, let's say, L.2, it's not possible to have L.2 of the data values less than it. We could get L of the data values less than it, but you can't get a part of a data value, like 0.2 of a data value less than it. So that's why we can't get an exact percentile for this data. So instead, the value of p sub k for the percentile is approximated by always looking to the next higher whole number location in the sorted list of data. So if our calculated L value was L.2, we then just go to the next larger whole number above L, in this case the L plus first data value in the sorted list, and use that value as our answer for the p sub k, the kth percentile. This gives us about k% of the data values less than the p sub k. And then the remaining data values gives us about 100 minus k% of the data that are greater than that p sub k. The reason it's not exactly k% less and the remaining 100 minus k% greater is because that percentile is equal to a data value in the particular list. So the percentage of the data values that is actually equal to that value is the result that doesn't give us the exact k% less than. Although in certain situations, or for specific sample sizes, the precise result for the kth percentile cannot be achieved, as long as the sample size is sufficiently large, this imprecision is negligible. On the other hand, when the sample size is fairly small, the approximation could yield a result that is somewhat inaccurate.